Hi all of you, and thanks for tuning in to this section of the DC20 Summit. My name is Jonathan and I'm part of the global product management team for contactors here at ABB Electrification. In this segment we're going to learn more about where DC contactors are needed and of course dig deeper in the ABB contactor portfolio for DC switching. So let's get started. The megatrends today moves towards a greener future where a lot of the energy production is and will be originating from a renewable source. We have seen this development traditionally within hydro and wind power, but in the recent years solar and battery storage have been on the uprising. Because of these trends there is a need for components that can handle the systems that are set up, and a lot of the component development have therefore been within direct current. This is something that has also been recognized by the IEC standardization organization. In 2018, they added the utilization categories DCPV3 and DCPV4, which are specified especially for PV solar power plants. These categories describe the typical requirements for an inverter-based application, where the inverter steers the current and the contactor will be used for isolation purposes and emergency braking, but also needs to withstand the heat from the power system itself and the current that flows through it. Some of the more common applications that we see today that require the DCPV3 category are the photovoltaic central inverters. The PV panels are only producing electricity during the day, and during the night a contactor on the DC side will isolate the panels from the grid, not allowing any power from the grid reaching back to the panels, but also allowing the inverter to do power compensation to the grid without any disturbances from any potential residue power coming from the panels at night. Another application is the battery's energy storage systems. What is set up is like the central inverter, but here the contactor needs to be able to isolate the battery sources from the inverter and capable of switching during both charging and discharging, making the bidirectionality of the contactor very important. For this purpose, a contactor is the perfect choice when it comes to having the capability of bidirectional frequent and reliable switching. Also, it's hard not to mention EV charging, which is on the uprising, especially for heavy vehicles and within the marine segment. where electrical ferries need charging or bigger vessels needs to be on auxiliary power while at harbor, our DC contactors are the perfect choice to control the power distribution. The applications for DC contactors are piling up, and ABB is a strong actor in this market with a complete portfolio of products for DC switching. The ABB offering for DC switching consists of 3 different ranges with different capabilities. Our full range goes up to 1500 volts and can handle currents up to 2650 amps. Let's take a deeper look at the 3 different ranges. First, the general range in AF, which have capability to switch up to 850 volts with time constant levels up to 7.5 milliseconds for the biggest sizes. In this range we have sizes to cover up to 2650 amps. The AF contactors are suitable for bidirectional switching. AF contactors is our main range and has been on the market several years, where the common application is of course within AC. But throughout the years we have been able to define the DC characteristics for these contactors, and today you will be able to find AF in both AC and DC applications. For systems where the requirements are a bit higher, we have introduced the GA and the GAF contactors. This range is designed to break up to 1000 volts DC. This range is available to switch DC-1 currents up to 2050 amps. The design of these contactors includes permanent magnets, which makes the contactor unidirectional, and the polarizations needs to be considered during installation. Lastly, we have our newest addition to the portfolio, the GF contactor. It's our 1500 volt solution. It has been designed and qualified to meet the requirements for the new utilization categories DCPV3 and DCPV4, which are specified especially for the DC inverter applications. And I'm happy to announce that we have recently launched the newest addition to that family, the GF1325, which is capable of handling bidirectional currents up to 1325 amps. The GF is available in 2 different coils with built-in PLC control and fitted with mirror auxiliary contacts, and it's a unique product on the DC market today. The innovation in handling the 1500 volt DC for the GF is explained by the double contact system, where we have 1 pair of arcing contacts and another pair of main contacts. Due to a cogwheel design, the arcing contacts will have much longer traveling distance and can stretch the arc over a higher number of splitter plates. At the same time, the main contact will travel a lesser distance, and therefore a more optimized magnet system can be used inside. All of these 3 ranges feature the ABB AF technology inside, which means that the coil control is handled by a PCBA inside of the contactor. The AF technology has been on the market for well over a decade, and it's a given standard for ABB contactors. It is well proven on the market and shows fantastic results. Using a PCBA gives us the capability of handling wide voltage operating coils, which have meant that we can reduce the number of coils to only 4 variants. And this leads to a great reduction in the number of product variants, which allows our customers to simplify the logistics, cutting storage and administration costs. The AF technology have also the feature that allows the contactor of working in an unstable network and thus can prevent stoppages. The contactors ensure distinct operation by being able to measure the incoming control signal and make a proper decision when the power is enough to close, unlike a purely mechanical construction. This also allows us to steer the power consumption of the coil to have the power output up to the magnet at its optimum at all time. The PCBA also features the built-in functionality to mitigate voltage sags, dips and surges in order to secure our customers' uptime. Here at the ABB factory in Västerås, we're building the next generation contactors to make sure that the right components for a direct current future is possible. At ABB, we have an over 100-year experience of designing and manufacturing contactors, and we've been driving the innovational steps and breaking new grounds throughout the years. In our portfolio, we have the products to cover the low voltage directive up to 1500 volt DC. Here we can see how the new 1500 volt GF contactor is being assembled manually in the factory, and how each contactor undergoes testing to ensure that high quality products are always leaving the factory. In 2019, the new low voltage laboratory was inaugurated just next to the factory. It is one of ABB's most advanced high power laboratories for low voltage products. It is capable of handling voltages up to 1000 volts AC and 1500 volts DC, and currents up to 20 kiloamps. With the location of the lab within walking distance from our R&D and factory, it gives us a great capability to find and test the best solutions for our customers. With this and the support structure that we have in place, it gives us the fantastic capability of handling all the inquiries that we get from our customers, which makes ABB a very strong player on the DC switching market and a great partner for your company to meet the new megatrends of the future within direct current. Thank you for your attention, and if you have any questions regarding contactors, please don't hesitate to initiate a contact with us. Thanks, goodbye, and stay healthy. Hi again. In this section of the contactor topic segment for the DC20 Summit, we're going to take a deeper look into how the traditional categories of use for DC have progressed into the modern world. And with me today, I've invited two of the experts that have been part of the contactor development through the last decades. And what better way of looking at the historical view than to film this session at the old ASEA headquarters here in Västerås. Thanks for joining.
For me, it started in the mid-90s with a corporate research project. Within ABB it was called a high impact project, but it was to develop electronic control of contactors. And I started it in the beginning. I thought that was quite a simple thing to do. It was far more complicated than I thought from the beginning. And it took us some time, but in the end of the 90s we released our first products with this technology. They were called the AF contactor, where AF means electronic control contactors.
Yes, my career started at ABB 15 years ago. I started at the R&D department in a product development project together with Gunnar, and learning to design contactors from scratch. So that project ended up with AF 116 to AF 370. Started as a design engineer and ended up as a project leader. Yes, starting with the older categories, they are very much focused on breaking or switching the full load current. But as we see, modern applications doesn't really have those requirements, and the risk, as I see it, if you choose a contactor based on the DC1 requirement, for example, which is switching resistive loads, is that first of all you could end up with an oversized product.
Okay.
And second of all, it might not even do the job for you. Then we need to start talking about critical currents. And you can define critical currents as current areas where it's difficult to break the current, because breaking the current is the difficult part about DC and DC contactors. And typically you have critical currents at 10-20% of the full load current, and that is around maybe 30, 50 or 70 amps. And these new requirements for these modern applications, for example, power transmission in a PV inverter, is very well captured in the new DC PV3 and DC PV4 categories.
Using a traditional electromechanical switching device, you normally have contacts made by some material somewhere. When you want to break the current, you open the contacts. What happens then is that an arc is created between the contacts. The current is broken first when the arc is extinguished. The normal technology is to let the arc, by its magnetic forces generated by itself, move into some kind of arc quenching device, like a splitter package, for instance. And then it is quenched and is extinguished and the current is broken. But for lower current, there are not magnetic forces high enough. So the arc will stay between the contact and it will not move away. And since there are no zero crossings, it will stay burning there until the device is destroyed. Yeah. So that is tricky. One of the very tricky things with breaking DC current.
Power transmission is done at full load current. Normal switching is done at a very much lower current, and for abnormal conditions, for example a short circuit, the contactor can break the current, but that is usually about 5-10% higher than the normal current. From what we can see, the requirement for example, battery energy storage is very similar to the PV inverter requirements. One major difference is, of course, the short circuit requirements, which is very much higher on battery energy storage. So there we need to use the contactor in combination with the short circuit protection device.
I can say that traditional devices, when they are breaking AC, they are using the zero crossings, because the current passes zero. And at the zero crossings, the current is prevented to reignite in the other direction. So the zero crossings are used in AC for breaking it. But for DC, there are no zero crossings. Instead, the contactor or the switching device has to create such a counter voltage so that the current is reduced to zero because of this counter voltage. And then when the current goes to zero, it is broken. You know? So that's kind of different requirements. And AC uses the zero crossings, and in DC, the counter voltage must be created by the switching device. Yeah. Of course, a standard AC contactor can break also DC because it can create a counter voltage, but only up to a certain level. that is normally lower than the AC braking performance. But especially when you are talking about lower current, as we have talked about critical current, that is also very difficult for it. But of course, ABB's devices can handle the critical current up to the defined rating.
Of course, AF contactors can break a DC current up to a specific voltage level, but if you want to go up a bit in voltage, for example 4000 volts, you need to use the GAF contactors. That one has the drawback that it can only break the current in one direction. Also, but if you want to go up to 1500 volts DC, which is the maximum for low voltage, you need to use the GF contactors, and that one also has the advantage of breaking the current in both directions.
I was actually asked to start this project some years ago, and at that time we started to get inquiries about 1500 volt DC, and we didn't have any products for it. So we started three activities a little bit in parallel. We started a market study, or a technology market study, to really figure out what they wanted, these customers. That was one thing. Another thing we started was a technology study to evaluate different technologies for doing this. And then the third thing was that we found that from this market study we found that the requirements in the standards were not really suitable. So we started an activity within the IEC to try to define new utilization categories more tailored for solar applications. These kind of utilization categories already existed for some other devices, but not for contactors. So we had three activities in parallel, and finally it ended up with this, the GF contactor, and also this standard.
Thank you.